AlgaeNano Plus is a startup student initiative from the University of Puerto Rico focused on scientific advancement, cutting-edge development, and STEM education using algae as our prime source.
Nowadays, the maximization of homeland production is critical for the sustainability of our industries. Using our natural resources such as algae not only tackles the problem of the overgrowth of seaweed on our shores affecting the tourism economy, but also presents an opportunity for the expansion of the supply chain.
AlgaeNano Plus proposals uses algae as an eco-friendly source of functionalized nanomaterials with a possible scalability production for a wide range of applications. We start by going to the beach. We collect some of the many algae that arrive at our coast and bring them to the lab to do some pretreatment process. Using a high-efficiency extraction technique, we analyze their composition to recover valuable compounds that can be used for several applications, and nothing goes to waste. Whatever is left is saved for more experiments.
This waste becomes our biomass for the vaporization process, where the different macroalgae are converted into biocarbon through a muffled furnace. The biocarbon obtained is characterized by different analysis techniques such as infrared spectroscopy, thermal gravimetric analysis, and gamma spectroscopy. We identify the functional group, electronic configuration, thermal stability, crystal structure, and other characteristics to identify the type of carbon generated and its purity. Part of our soil remediation project to improve the agricultural industry, we created a metal-contaminated profile for the proposal of evaluating the performance of algae-based graphene oxide in reduction of copper and iron. The preliminary result demonstrated that the graphene oxide of urban algae have a 96% of capacity to reduce copper ion. Additionally, the graphene oxide from Brachiaria algae have a 94% of capacity to reduce the lead ion. The aim is to use the algae-based graphene oxide for the development of agrotextiles that remove contaminants while protecting crops from common problems such as pests, invasive plants, drought, and improving agricultural soil.
To assess whether the algae biocarbon was suitable for a biosensor device, we tested its electrochemical potential.
For our electrochemical experiments, we receive a pre-treated calcinated algae as our precursor for graphene.
We explored two oxidation methods. They, however, rely on strong acids and expensive reagents, which increases cost and raises safety and environmental concerns.
For this reason, we want to explore other alternatives. Among these are biocarbons derived from algae, which have been evaluated for their good conductivity properties and similarity to reduced graphene oxide, a good conductor that has functional groups needed for biosensors.
We determined the conductivity of the biocarbon using electrochemical techniques like voltammetry.
So, we observed that the biocarbon shares similar properties to reduced graphene oxides because of its substantial literature as a biosensor transducer.
Graphene oxide is commonly reduced to its functional groups to have better conductivity and also small functional groups that will help attach probes.
Derived from natural renewable sources, biocarbons exhibit good conductive properties and can be directly applied in biosensors without the need for extensive post-processing.
As for the energy storage applications, our process begins with the reception of dry algae, which is then subjected to pyrolysis at various temperatures to evaluate the performance of algae-derived hard carbon as a cathode material.
We make a slurry for that carbon and we mix the binder into it. We deposit that slurry onto the copper foil, cut into the form of the cathode, and we can use in assembling the battery.
Due to some properties that this material it has a high electronic conductivity and porosity, so it means that the material itself has a large surface area, which allows, due to the high electronic conductivity, high flowability of electrons.
The capacity was like around 300, so it is more comparable with the commercial graphite.
Instead of buying a commercial black carbon, hard carbon, Ketchum black, we are stepping over relying to foreign sources.
It's very costly to mine the graphite, and the total outcome is like it's very expensive. So to avoid that, I think the biocarbon, this is the more sustainable, more eco-friendly for the use of the battery.
So the idea is to build a fully based algae battery, both the electrodes, electrolyte, and the casing.
We use our research to engage with the community and promote rural outreach, including school students and teachers. We invite them to our laboratory and conduct workshops to demonstrate how algae, chemistry, and science can drive innovation and prepare them for the workforce.
As a team of qualified scientists, We aim to advance groundbreaking science toward a more resilient, independent, and sustainable future. We strive to demonstrate that even with algae, we can inspire students to pursue STEM careers, equip them to face the challenges of our generation, to innovate.